There are two examples at the end of your 3.2 packet that I want to go over. This problem from the first example, some of you saw this picture on your limits and continuity test. We've been asked to name all the x values at which f is not differentiable. Well, there's sort of two big categories. F is not differentiable any place f is not continuous. So can we name all the points of discontinuity? This is what I have here. So I say f of x is not differentiable at x equals -1, at 0, or at 2, because f of x is not continuous at x equals -1, 0, or 2. At x equals -1, there's an infinite discontinuity. At x equals 0, there's a removable discontinuity. And at x equals 2, there is a jump discontinuity. So it's enough to say, it's enough to justify your answer that f is not differentiable by claiming that f is not continuous. Okay, I think there's one other place where f of x is not differentiable. It's a place where it is continuous, and it's here. Let's see. This is my hint, the corner. So here's what I would write. I think f is not differentiable at x equals 1. If I was explaining to my baby brother, I'd say because there's a corner. But I want to write the actual justification using the definition of differentiability. So give me a second, I'm going to type that up. So here's my justification. I say f of x is not differentiable at x equals 1 because I know the limit of the derivative as x approaches 1 from the left is going to have to equal the limit of the derivative as x approaches 1 from the right. Watch here. As I approach 1 from the left, I'm coming along this piece. It's a little linear piece of my piecewise function. I can tell the slope is positive. So the derivative must be positive. As I approach from the right, I'm approaching along that little linear piece whose slope is obviously negative. So I'm going to have two different derivatives, the notation, because the limit as x approaches 1 from the left of f of x minus f of 1 over x minus 1. Remember, that's our alternative definition for the derivative at a point, is not equal to the limit as x approaches 1 from the right of f of x minus f of 1, hope it fits, all over x minus 1. And if somebody pushed me, I'd say, I know that the limit as x approaches 1 from the left of this expression, but the expression for the derivative, must be positive. And I know this limit on the other side, the limit as x approaches 1 from the right of f of x minus f of 1 over x minus 1, the derivative from the right, must be negative. Therefore, I know they cannot be equal. There's one more example down at the bottom. Oh, you can't see the example. Alright, so you'll have to follow along on your paper. My question, we have a piecewise function, f of x. My question is that x equals 3, is f of x continuous? And then, if it is it also differentiable? So a function is continuous if its limit from the left equals its limit from the right equals the actual function value. So here we go, I've got the limit from the left is going to be x squared, but with x equals 3, so 3 squared. It's going to have to equal the limit from the right at x equals 3, which is 6 times 3 minus 9. This is 9 equals 18 minus 9. Okay, so the two limits are equal, and the actual function value is one of those 9s, so the function is continuous. You have to tune into the next video to see if it's differentiable.